encoded architectures part 2. Okay. So yes, indeed, it's just a continuation from where we left basically yesterday. So we're again in the topic in the context of physics encoded architectures. Yeah, so second block here. Yeah, indeed. Let's unveil the second block here, which is sorry, no, I had to continue on the past one. Sorry, wrong chapter. It's still physics encoded part 1. My fault. Yes. So indeed, yeah, we're always here. Let me maybe scroll quickly to the part that we where we left from yesterday, which is this one. So you have the slides already, by the way, in the Google Drive folder. So yes, the second block here is neural ODEs, what we call NODE. So NODE stands for Neural Ordinary Differential Equations and Variational Integrators. So here the motivation, the slogan is to try to learn the dynamics via structure-preserving integration, especially for the case of variational integrators. But here the idea is also very simple. So basically you have your physical system that is described maybe by some ordinary differential equations in this form. We just want to use a neural network to learn this form. Okay, so without injecting too much physical information, maybe we just want to use a neural network to learn the right-hand side here. This is called the neural differential equation. And then we need to integrate the equation numerically, and we can do this by some variational integrators that tend to preserve more structure than general purpose integrators. Let's have a closer look. Yes, let's start from what we call neural ODEs, NODEs. In this case, yeah, okay, it's taken from a paper in NeurIPS 2018. And the idea here is to start from a continuous time ordinary differential equation of this form, yeah, very general, where h is the state basically, and it can depend on time and on some parameters theta. And neural ordinary differential equations simply mean let's use a neural network to learn the right-hand side. Okay, so let's substitute h with a neural network. Fine, yeah, very simple. But then the issue is, okay, no, and you can, this is the continuous time version. There is also the discrete time version if we rewrite the ODE in discrete time. And this is commonly called a residual network. Okay, so it's still a NODE if you want. It's still a neural ordinary differential equation, but in discrete time. And then it becomes a residual network, right? Because you have you just want to learn the residual f that brings ht to the next time step. So ideally, ht will be very close to ht plus 1, right? In one time step, you cannot change a lot. So it's like a residual that you want to learn. Also related to residual networks, yeah, in the literature, to ResNets. But yeah, it's just the discrete time version of a neural ODE. And you see it also in the picture here, right? The discrete version versus the continuous time version in the terms of flow representations. And indeed, here for our neural ODE, the loss function can be, so how do we learn actually the function f, the neural network f? For example, supervised learning, yeah? So we minimize the deviation between age.
What we can say, as if you go back to one thing.
Yeah.
So are the two possible approaches, no? So one is the continuous time when you learn the derivative of the system. The other one that you learn the residual. Commonly, what you do is something like this, no? Because the part related to the integration is commonly more tricky, is a more complex algorithm to implement. So commonly when you implement classical integration, you do this and you learn this residual network. Of course, doing this, commonly the network learn fixed steps in time. Okay. Instead, using the continuous approach, you can sample the system in as much font you want. Okay. So this is important to take into account.
Indeed, yeah, there is a difference, but still in neural ODEs, people want to try to keep it in continuous time.
Yeah.
This is the work of neural ODEs. They want to keep it in continuous time, but then indeed, if this is the loss function, so the measurement h maybe h hat minus your real state h. Okay, if this is the loss function, then, okay, this is a simple backpropagation rule, right? If you take gradient-based learning, vanilla case, yeah, very simplified, then you have that theta k plus 1, so the parameters of your neural network theta, k plus 1 is equal to theta k minus a certain learning rate, or minus a certain step size, if you want, eta, times your nabla L, so the gradient of the loss function. So this is simple gradient descent, yeah, in its simplest form, yeah, of course. Indeed, that f is parameterized by theta. But now the challenge is how to backpropagate nabla L, so the gradient, through an ODE solver, because an ODE solver could be also very complex. If you think, I mean, you can use Runge-Kutta, you can use variable step solvers, so it can have a lot of operations, and backpropagating the gradients through all these operations can be a bit tricky. So the idea of neural ODEs, without getting into technical details, is to use automatical differentiation. So basically to use the adjoint sensitivity method for automatic differentiation to get an efficient expression of the gradient of nabla L. And this applies, by the way, to any ODE solver they showed in their paper. So Euler, Runge-Kutta, and other type of integrators. It actually scales linearly with the problem size, so with the number of nodes, if you want, or collocation points. Has a relatively low memory cost and provides also numerical error control. So basically, this is the technique that people use to actually train neural ODEs with automatic differentiation and the adjoint method in particular for automatic differentiation. And this is implemented in some libraries that we will see probably tomorrow or on Friday. So you don't need to care too much about this. This is implemented in basically in PyTorch-based libraries. And then the second part, okay, so this is the way in which we can learn an ODE from data, basically. If you want, you can also try to open the black box here a bit more. So instead of using a multi-layer perceptron, you can start plugging in more physics priors. It can still be called a neural ODE if it remains in continuous time. So yes, but in the classical setting, at least for this paper, they didn't give so much structure to the neural network. So it's a general purpose approach, yeah?
Say another things related to the difference between this network and the other. Here the time is embedded inside the network. So the network learn a specific time step. Okay, so when you learn this, you decide what is your step, and the network learn your step, your time step. Instead, here the time is an input of the network. Okay.
Yes.
So the time is an input of the network, so you can sample your working space, your domain in any time, in any position X or time that you want, that you have collected data. But remember that the input of the network is also the time. Okay, so the solution that you find here depends on time.
Yes, the time can be an additional input
to
the neural network, or actually is an additional input in the data.
This approach is an additional input.
Exactly. Yeah. And indeed, so in this way we can learn an ODE from data. And then the next question is, okay, this is still in continuous time. How do we solve at the end the ODE? we need to solve it numerically most of the time, especially if we use a neural network there. So, okay, we can still use Runge-Kutta Euler, but okay, some people said, let's also have a look at these variational integrator networks, what actually they do. Again, without entering into too many details, but if you can use Euler or Runge-Kutta, but the problem is they may not preserve the structure of the problem, like the geometric constraints or energy properties of the system. So it may still happen that you lose some energy with these traditional methods when integrating a physical system. So the idea of variational integrators and variational integrator networks, VINs, is instead to use some symplectic integrators, they call them. So some structure preserving integrators that have a particular structure and that can preserve then the properties of the system. So they can actually approximate, they can approximately conserve energy and momentum with a higher, to a higher order, for example, to third order or higher, because of how they are designed. Okay, so there are particular types of variational integrators in the literature already available. Okay, you don't need to, you just need to find the best one that suits your application. And this one can really help preserving energy better than Runge-Kutta or Euler. And so this is simply what at the end the integrator does, right? So you have your system from your initial coordinates that is recursively integrated over time. And to do these operations, we can use these variational integrators. And there are some papers, for example, this one, in which they show that actually using a variational integrator has some advantages. For example, in the case of a simple mass spring system without friction. So here, again, you should conserve energy indefinitely over time because there's no friction. And you have noisy observations, Q, P. So again, P is the momentum, Q is the position of the mass in that case. And also Q dot P dot. So you have noisy measurements and a small training data sets. Then also Hamiltonian neural networks here in blue, they actually tend to lose energy. So we said, okay, they tend to actually conserve energy in the ideal setting if the data set is big enough. But then people showed, no, actually also Hamiltonian neural networks can lose energy. And to do better than Hamiltonian neural networks, you can use them in combination with a variational integrator, like in this case. And then if you see in green here, the system in the phase portrait, QP, and also in the evolution of energy over time, you see the variational integrator in green doesn't lose energy, or loses way less energy than the Hamiltonian. And also in terms of error, RMSE on the coordinates, it performs better also than a baseline neural network. Yeah, here, interestingly, the baseline outperforms the Hamiltonian, which is a bit strange, but in certain settings, they still can happen.
Use variational integrator for the baseline, no?
No, they didn't. But they say in this case, the Hamilton. So the thing is, this is a test data set, okay? This is not the training data set. So this is an unseen test data set. And in this case, the Hamiltonian was, they say, that the Hamiltonian was overfitting the training data set, the Hamiltonian network, while the baseline was able to somehow generalize better. It can be a case, okay? It can be just due to their particular choice of configurations. In the case of a medium training data set, actually you see still the Hamiltonian and the baseline perform similarly. The variation integrator performs a bit better, at least in terms of accuracy, also in terms of energy. But yeah, you see, especially in the case of small training data sets, it may be that Hamiltonian still overfit, and then they generalize badly. And then combining them with the variation integrators can help. Yes, okay, so this is what we said. This is, again, also in the case of a frictionless pendulum, same conclusions as before. Small data sets, the Hamiltonian tends to overfit and lose energy, or no, okay, energy maybe, yeah, it's still, it actually gains probably energy in this case, while the VIN tends to keep it more constant, and the baseline is actually losing energy. While with a medium data set, things go a bit better, but still the VIN turns out to be the best in this case.
See, in that case, the baseline gain energy. No?
Yeah, exactly. In this case,
as I mentioned yesterday, it's not sure that you lose energy, no? Because if you fit the Q dot, I mean, you can just estimate a little bit more than what must be, and then you gain energy. So
yes. So in this case, you can gain or lose energy over time. But if you do things carefully, Hamiltonian plus VINs plus whatever, then you can make things a little bit better.
Yeah, what I can say, if you do the training and you impose not only the derivative but the position or the value, commonly what I have seen so far, you lose a little bit of energy. So if you integrate your value also with using a very simple integrator, not variation, not inside just Euler. And you integrate, but you impose not only Q dot, but Q, commonly what's happening is that you lose a little bit of energy, because otherwise, if you take a sufficient long horizon, commonly you lose energy because the opposite will be more dangerous, and the network prefer to avoid the case that explode the value. Commonly this is happening.
Yes.
Because these are trained with not imposing a window, we're just imposing the value.
Probably they are trained on the instantaneous values. But the thing is, so indeed, so Gastone is saying that if you gain energy over time, then you may enter instability somewhere in the future. While if you lose energy, then the system is more stable, right? So even the loss function remains bounded, So while if you gain energy over time, the loss function will explode somewhere in the future. And this is not what the backpropagation wants to do, Right. Okay, so here different approaches, but which one should we choose? I mean, depending on our application use case. Well, the people that presented Lagrangian neural networks also made this nice table that summarizes the pros and cons. So basically, if we have physics priors available, then we can choose a set of approaches. If we don't have physics priors, well, the thing we can do, probably the only thing we can do is a neural network, right? A very general purpose neural network, if we don't have physics priors. If we have physics priors, then we can use neural ODEs, we can use Hamiltonian, deep Lagrangian, whatever. Okay, there it opens more possibilities. Then if we want to learn differential equations, again, neural ODEs are a good choice. If they are ordinary differential equations, they are a good choice. But again, also the other approaches may be suited depending on the type of differential equation, if it's a Lagrangian, if it's a Hamiltonian. But let's say neural ODEs are very general purpose to learn differential equations. Then is energy conservation important in our case? If it is, then maybe neural ODEs alone are are not the best. But Hamiltonian and Lagrangian neural networks may be a better fit in this case, or variational integrators, as we've learned. And finally, is the structure of the Lagrangian known in advance or not? If it's not, I mean, if it is, and it is maybe a rigid body type, then deep Lagrangian can be the best way, because we know the structure of the Lagrangian. If it's not, so if it's a more general system, then and we still want to learn the Lagrangian, then LNNs, so Lagrangian neural networks, are the best option. And you see, it learns arbitrary Lagrangian, it learns from arbitrary coordinates. This is also important. So LNNs basically have all the ticks here, because Hamiltonians cannot learn from arbitrary coordinates, right? They require a P and Q, so the coordinates and momenta.
When they do the example from the pixels, I don't know. I mean, if you use an encoding.
Yes, indeed. So it's a bit borderline, of course. So you can still give the momenta a very general meaning, yeah, if it works. So yes, indeed, in principle, Hamiltonians and Lagrangian act similarly. I mean, they both learn a function, yeah, either Hamiltonian or Lagrangian from data, and conserve energy. But indeed, the momenta for Hamiltonians can be tricky to formulate, at least if you want to give them a physical meaning. Yeah. So this can be a bottleneck. At least this is what people often say in the literature for physical systems. And so in this case, LNNs can be, Lagrangian neural networks can be more general and powerful. Of course, this description is a bit biased towards Lagrangian neural networks, but in your application, I don't want to say these are the best. So it depends a lot on your system and what you know about the Lagrangian, what you know about the system in general. Yeah. Questions here?
I can say from my experience, perceive the Neural ODE is a very powerful tool in general, because you don't need to formulate in any way your system. I mean, you can use any function and just plug in a Neural ODE for the integration part, and you are very free to use what kind of network you want. So I think one most powerful approach can be the Neural ODE. That is very flexible.
Yes. It's also very common in the literature, yeah. So you find also many open source libraries that support Neural ODEs, so you can actually use them. Maybe we'll show you something in the next days. Yeah, so indeed, these are powerful tools, not only if you have complex partial differential equations to solve, yeah. So let's think that they can be applied also to your research, probably, yeah. Okay, so this concludes this chapter, the part 1. Then we can maybe introduce part 2 briefly, then we can take a break and continue. So yes, this is just the continuation from where we left, always in the architecture. We just described the first 2 blocks, so Lagrangian, Hamiltonian, and neural ODEs. The third block here is what we call hybrid approaches, which means basically a lot of things. Hybrid physics neural approaches. But we can be a bit more precise, okay, what we mean by hybrid physics neural approaches. So here we collect a bunch of approaches that basically treat neural networks as modules. Okay, so we have a modular combination of physics-based models and neural networks, or machine learning in general, models. So indeed, it's a modular combination. So they are separate modules, yeah. They are still not part of the, so we don't want to open their black box, let's say. So neural networks in this case remain, if you want, black box models or very general modules, no physics inside their architecture, but we combine them with physics-based models. So for example, we inject them inside some equations. So indeed, our aims here are to correct physical models. Maybe we have a physical model that works 90% of the cases very well, but we want to fill the remaining 10%, and then we use residual learning. Yeah, so physics plus neural network is the first use case. Second use case is learn specific parts of the system, specific subsystems, yeah, which is what we call subsystems learning. So we have basically a physical model, but we have some components inside that are hard to model physically. tires, gearboxes, whatever, of your physical system. And then this is an example, okay? So we use a learning model to do better than what we can do with our physics alone, without losing the physical information. And finally, okay, the final category is the one in which we want to pre-process sensory data. So we have sensor data, can be cameras, IMUs, whatever. We use a neural network to pre-process them. Like if it's a camera, we use a convolutional neural network, whatever, to pre-process them, and then we feed the output to a physics-based model. Okay. So in all these applications, you see they are modular approaches. Yeah. So we have neural modules, and then we have physics-based modules. It's just a matter of how we stack them together at the end, how we combine them without losing possibly interpretability and physical meaning. Okay, and we're going to focus briefly on the first two, which are very common, yeah, in the literature, I would say. The first one is residual learning. Yes, indeed, a very popular and powerful approach. Also very simple to implement.
No.
Which temperature? Yeah, of the projector. Okay, projector is overheating. Hopefully not. So the idea here is very simple to implement. And the idea is to learn the discrepancies between a physics-based model and the real-world data that you may have. Okay, so the physics model is not perfect. It may have model mismatches, parameter uncertainties, whatever. So we simply use maybe our sensors information. We feed them both to a physics-based model and to a very general machine learning model. It can be neural network, Gaussian process regression, whatever. And finally, what we do, we simply sum them. Okay, we take the sum of the two, and this is the output. Okay, very simple idea. Historically, actually, one of the first probably to be implemented as examples of, if you want, merging physics and data together without too much effort. Very powerful in the community, especially of robotics, but in general, yeah, mechanical systems, electrical systems, very powerful and very popular. Yeah, we can have, for example, a look at this use case from 2019. It's a use case in autonomous vehicle racing from ETH. In this case, they wanted to learn the residuals. So they had a physics-based model. In this case, it was a single track model, for those of you who know a little bit in vehicle dynamics. So a very simple model, but it was imperfect. Yeah, so it's hard to capture the vehicle dynamics at the limits with this type of model. So they said, okay, let's use this model. Do not throw it away. Single track model is F, what we call F, with in this case 8 states. And then they said, okay, let's use a Gaussian process regression, GPR, to learn its residuals based on real world data. And GPR is something that combines basically Gaussians as basis functions, learns to combine Gaussians to obtain a better fit to your data. And it's powerful. I mean, they used it inside an MPC controller. So they plugged the resulting model, this model here, they were plugging it inside an MPC controller, right? Inside the dynamics, the prediction model of the model predictive controller. And then they had, of course, a cost function, constraints, all the rest. And they were using it actually to do online learning. So they were learning online the residuals. So this part here was learned online. The physics-based part was kept fixed. The other part, it was actually learned online using a dictionary of data points that were added as the vehicle was driving on their race line. And this resulted in a huge improvement of performance. You see the difference in the velocity profiles. So in red, the learning-based MPC could drive way faster. and it resulted in a 10% lap improvement. Yeah, this paper is very popular. There's also a YouTube video, very nice, with a lot of views. So they're really, it's a nice example of residual learning, I think, in autonomous racing. And then the second use case is subsystems learning, which is still related to residual learning. But here the idea is a bit more, if you want, a bit more complex than residual learning. So we have, it's still modular, okay? So we are still injecting the neural network somewhere in our physical model, inside our physical model. So we have maybe different parts of our physics-based model that are interacting with a learning-based component. And why do we do that? Well, because maybe parameterizing this subsystem can be a bit tricky, a bit expensive, yeah, time-consuming, requiring expertise. So we just want to simplify the process and maybe potentially also do better than what we can do with the traditional parameterization or system identification. Indeed, so this part of the system remains then data-driven, okay? The neural part is data-driven now. The rest of the system remains physics-based, interpretable, debuggable, whatever, okay? And examples of subsystem learning, well, some of you, I think, have used this approach already or know something about, for example, tire models, again, in vehicles. They are challenging to model otherwise with analytical or heuristic models. Also in manipulators, we often have robot manipulators. We often have gearboxes like harmonic drives or epicyclic gearboxes, and modeling them analytically can be challenging because we always have a backlash, we always have friction, fluids inside. So yeah, this is also a nice example of complex subsystems. But again, the rest of the robot manipulator is maybe easier to model from Lagrangian or Newtonian approaches. And I want to give you just an example, again, in the context of vehicles, velocity estimation. So here they wanted to learn the dynamics of a vehicle, again, starting from a physics-based model, 4 states. Basically, the states are the longitudinal velocity, Vx, lateral velocity. These are Newton equations, very simple. The yaw rate R, this is the Euler equation for the rotation. And then the omega s, which was the engine speed, I think. And again, identifying here, you see there are a lot of tire forces, okay? Fx, Fy, F stands for front axle, R stands for rear axle. But identifying these forces, Fx is longitudinal, Fy is lateral. Identifying them can be tricky with real-world data. So what they said, and also can be tricky, but also requires, if you want to do it well, it also requires a tire test rig, which is a very expensive machine, hard to maintain. Only, I think, 3 places in Europe have it. So it's really a challenge to do that. And so they said, let's use neural networks to learn the tire forces. And so they were using basically, yeah, general purpose networks as a function of their states X and controls U to learn these 4 tire forces. But the rest of the model remains physics-based, yeah? So it's still analytical, plus these neural corrections. And they were actually integrating the model inside an unscented Kalman filter for velocity estimation at the end, or state estimation more in general, if you want. So basically they had, yeah, so the vehicle model was integrated inside the prediction model. If you're familiar with Kalman filters, we always have a prediction and an update step. In the prediction step, they injected this vehicle model containing the neural tire model to estimate the predicted state and covariance P of the estimation error. And then they were taking a standard UKF update, Kalman filter update, and then propagating everything back. And here the trainable part was the entire model. Okay, you see, they wanted to compute the gradient of that with respect to F, but also the covariances, Q and R. This is more classical in the Kalman filter. You have to learn the covariances, Q and R, for the process noise and measurement errors. And at the end, they had their loss function computed with their measured data. So this is standard supervised learning. So measurements against model predictions. And they were training this sort of end-to-end, probably, right? So they were training the model inside the Kalman filter. And they were showing they could outperform general purpose networks. So instead of using an analytical model containing neural tire models, they probably used the GRUs and LSTMs, which are very general purpose neural networks, which typically were presented in the context of natural language processing, but then people apply them also to physical systems. But yes, because indeed they are general, but they could overfit. Yeah, this is the problem. Yeah, they have a lot of parameters. Typically, they overfit. This is what happens here, probably. So this is the lateral velocity Vy. You see in red the estimate of their UKF is better than the benchmarks. And they also show the zero-shot generalization to unseen scenarios.
We want to just say a word regarding the LSTM and GRU, that are networks that were designed for text. Okay. Yeah. And they have the capability to remember something that happens hundreds of steps before. Because, for example, if you write code, if you open a bracket, then you need to close some moment. No? So, but apply those networks for physics can be dangerous, because commonly an effect that you do now is not propagating over time for ages. No, at some point it's just completely unuseful. No, so that the input. So yeah, I think the idea to use something more physical is, I mean, have sense. No, it's something that is smart. No, because using standard networks is dangerous, because the structure were thought for a specific task, was remembering text, and the text have this property that if you open a bracket you need to close, and doesn't matter how many lines you wrote. No, yeah, at some point you need to close the bracket, and LSTM and GRU have this gate. No, so the gate can still activated for many cycles. If you apply instead a more physical approach, when you apply a gas pedal, then at some point the application of a gas pedal now is not anymore something that you get out from the network. No, so this is something that is have a meaning, have a physical meaning that the other two networks have not. No, so yeah.
Yes.
Just to make an idea of I mean, for me is not the right way to apply neural networks for in a physical system, because those networks are thought for a completely different topic, completely different. Then, because thanks to their capability, they are very flexible and they may work some way, but yeah.
In the same way, there is people applying now transformers and diffusion models to learn the vehicle dynamics. Of course, these models again were not conceived for physical system learning. They were maybe conceived for image generation or for tech or natural language processing, but still they are somehow general purpose, so you can apply them. But most of the cases you get overfitting, in comparison to combining physics and data in a more structured way, at least in our experience. Yes. Good. So questions here? Yeah, we can then.
Yeah.
So if there are questions, please feel free. So yes, we can continue. And we said, okay, so up to now we explored the first three categories for physics encoded learning architectures. I want to briefly mention the next two before moving on to the final one. So here, yeah, the fourth category is physics encoded topology learning. Here I don't want to get into the details, but the idea, okay, the slogan is learning connectivity from physics priors. So here you really want to learn the connectivity of the neural network. So the topology, the connections of the neural network. Do we build certain connections or not, depending if it's good or not to do that? So here there is a bunch of approaches to do that. Some of them take the name of equation learning. So you basically discover new equations through the neural network. This is very fascinating if you want. So you can have actually the neural network that tells you, hey, look, this is actually a good equation that you should use to model your system. So traditional neural networks are not discovering equations. Yeah, they're just fitting data, finding the best fit for your data. These approaches, instead, they want to discover equations to fit your data. So basically what they do, so there's no magic there. It's just taking a library of functions that you think are good candidates for doing that. So for example, it can be trigonometric, cosine, sine, tan H, but also operations like sums, multiplications, divisions, whatever. Yeah. And so you tell your model, these are my candidates. These are typically called candidate functions or dictionary or library of candidates. And then the neural network learns basically what is the weight, the best weight to be given to that function. So if the network wants to basically activate your function or not, depending on your data. And here the physics priors can be integrated in the way you design these functions. So basically, if you know that you have a manipulator, a robot manipulator, whose dynamics depends or can be written as a combination of trigonometric functions, then you know you will need the trigonometric functions. Yeah? So sine, cosine, etc. And you can use them in your dictionary. And then the neural network will tell you, okay, which of them are actually meaningful, and it will also tell you in which way you should combine them. Another meaningful approach for this is SINDI. It's called SINDI, which is a very well-known approach, which is sparse identification for nonlinear systems. And it's based on the same idea. So just take your data, in that case in the time domain, a long matrix of data, and you want to fit them using a long matrix of candidate functions. And then you have a long matrix of weights that tell you which of the functions are activated or not. Basically, this is the idea. So here I don't have slides, but I just wanted to give you the intuition behind.
And for example, for the equation learner, you can also here is show just one single layer, but you can think that you can put as many layers as you want. Okay, creating a chain of your activation function, and during the training, when you commonly this is does in is done in supervised learning.
Yes.
You have a ground truth, and when you propagate, then the network decide which is the best candidate in this specific layer. In the paper that was presenting the equation learner, they also use a trick during the training as regarding the training physics training. They after a certain number of epochs, they just they done what to say they remove the unused activation function to help the network to focus on the one that were more active. Okay, so after hundreds of epochs, you stop the training, you have a look to the weights, and you say, okay, 10H is not used at that specific level, I will remove. So you reduce the number of weights and also help the network to focus on the right one. Yeah.
Yes, indeed. Yeah. So yeah, we don't want to go into the details, but still it's a meaningful approach. And again, you can incorporate physics priors by deciding which functions you put in your dictionary. The final approach I want to present shortly is neural operators. This is actually a huge field. I don't know if some of you have heard of that already, but it's also going up in the literature in the field. But conceptually, they are different from neural networks, right? So they also tend to have, or at least some of them have their universal approximation theorem. So they're not based on multi-layer perceptrons. The idea is that neural networks learn from fixed sized or fixed dimensional mappings of inputs and data. So you map an input to an output. Neural operators don't map data to data, but rather functions to functions. So they can choose in a function space of inputs and outputs. I don't want to get into the details, but it's also a powerful tool based on strong mathematical foundations. Maybe the most popular approach, and I think you heard of this, is Koopman neural networks. Koopman neural networks are very hyped in this moment. If you go to conferences, I'm sure you will meet somebody that does Koopman networks applied to some fields. So it's the most popular. It's a type of neural operator based on the Koopman operator, and then people build the Koopman neural networks. But there are also others, yeah. So I think you were mentioning yesterday Kolmogorov-Arnold networks. This is another type of operator, also getting popularity, even though it's also very complex, yeah, to understand and use carefully. Then there's also deep nets, also gaining popularity, I have to say. For example, we've seen some examples in vehicle dynamics. So some people were using deep nets to learn the dynamics of a vehicle. Graph neural operators and other ones, Fourier neural operators, and so on. Let me maybe give you some insights in how to incorporate physics in neural operators. Again, very, very broadly. For example, in the Koopman operator, what they do is in the Koopman networks, but also generally Koopman operator, the idea is that in some high dimensional space, can be very high dimensional, but there exists a high dimensional space in which your system dynamics that can be very nonlinear. Well, your system dynamics in this high dimensional space becomes linear. So now the problem is, or approximately linear. Now the problem is finding the functions that map your initial domain in which the function is nonlinear, can be Rn, okay, with n is your dimension. You need to map this space to another space in which the function becomes linear. And you need to use some lifting functions, again, also called dictionary, also in this case, to do the operation, to do the linear mapping. And then once you are in the linear space, the game is done, because then we have a lot of control methods developed for linear systems. Also MPC with linear systems is very nice. So the tool is actually powerful, yeah, because it lets you transform your linear system into a linear one. But you need the lifting functions, and the lifting functions is a sort of encoder, if you want, that encodes your nonlinear space into a linear one. And then in principle, you also need to decode, okay? So you can then let the system evolve in the linear space, and then you need to decode with another neural network, if you want, or another bunch of functions to go back to your original nonlinear space. And a way to incorporate physics priors is, again, in the lifting functions. Similarly, if you want to topology learning. So if you know your system is based on trigonometric functions, but you don't know how, then you can use trigonometric functions also as lifting operators. very broadly. You find some approaches in the literature, also about physics-informed Koopman networks, neural operators. Again, they don't do anything super fancy to incorporate physics. I think here there's still a lot to be done. So they present some approaches that somehow go in the direction of incorporating physics, but very, very preliminarily, I have to say. But this is still an interesting field, and again, it's very hyped in this moment. Questions here? Otherwise, if there's no questions, also from online, we can move maybe to the final part for today, and to the final chapter about physics encoded architectures. So this is the part 3 of this chapter on physics encoded architectures, and here we talk about something that we do basically in our group. So in our group in Trento with Professor Pappini, also where I'm now in my lab in Munich. So we collaborate a lot on these topics, and we call this approach model structured learning. And let's see what we actually mean. So of course, we're always in the field of architectures, physics encoded architectures, and it's the final block that we unveil here. And the idea, or our slogan, is to basically encode physics-based layers. As you can see very schematically from here, we have some layers that encode physics. We also have connections that encode physics, and we also have constraints that encode physics. Everything is inside the architecture. Okay, so everything needs to lie inside the architecture. And these are the basic ideas. So yeah, and the term model structured neural networks was introduced actually by us in some recent papers, which we summarize here. But we would like to, so these papers are in the field of vehicle dynamics, if you want. But we want to be actually general and cover a broader class of approaches that we're going to see now in this chapter.
These are the more recent.
Yeah, these are the more recent. Yeah,
exactly. When we started to use the name. Yes. But of course, there are some more older papers.
Yeah, these are some examples. Yeah, but actually, so we introduced this term now because we realized that this class of approaches could not fit into one of the pre-existing categories. So we decided to introduce a new term, and now we will explain what it means actually. So again, there are some general principles that we would like to have for our category. And these principles are, again, physics-based layers. So we can have actually neural networks, if you want, with different layers. And each layer, like in this case, for example, like each layer could encode some physics equations or principles. So in this case, this example is from the field of vehicle dynamics. The inputs are the velocity at time step k, and the pedal, if you want, the throttle or brake pedal of your car. And we have different layers, in this case, 3 layers. Each layer is modeling or is learning one particular force. This is the drag force, the aerodynamic drag force. This is the longitudinal force at the rear axle and at the front axle. So we have, you see, 3 layers. This is already a separation, like we know what each layer is modeling or is learning. And in the case of the drag layer, the first one, we know from physics that it depends on the square of the velocity, right? So instead of using Vx directly, we take the square, and then we use some type of neural network here. We can give more structure to that as well to actually return our arrow drag. And the same for the forces, right? For the other forces. So for example, the
We know our car is front, if you want, front wheel steering. Sorry, front wheel drive. So the torque of the motor goes to the front axle, while the braking torque goes, for example, to the rear axle. And then if we want to model so the rear axle receives only braking torque, and the braking torque is proportional only to the brake pedal, okay, and not to the throttle pedal. And so we can decide to, if P is our pedal variable with negative values indicating braking and positive values indicating throttle, acceleration, then we can extract only the negative values, so the braking values, feed them to our braking neural network and compute the braking force at the rear axle. So if you want, this is a way to tell the neural network, hey, look, these are not generic variables. They're variables that represent physical quantities. So we have some ways to preprocess them and then learn their effect on the dynamics. This is just an example, yeah, of course. So this is layers. Then we have physics-based connections. So how to connect actually the three forces? Well, Newton tells us the forces are additive, they superimpose, okay, their effects are superimposed. And so the simplest way we can do is just to sum them, right? This is superposition of forces. So yes, this is a simple way to have physics-based connections. We can also have other types of connections, yeah, symmetries, whatever. And then the last part is constraints. So what about we know that some values in our model, in our neural network, are interpretable? So we can give them a physical meaning, and if we can give them a physical meaning, maybe we also have in mind a range for their values, yeah? For example, the aerodynamic drag, we would like to be only positive. Or, I don't know, some parameters, the mass is strictly positive, because otherwise it may happen that your neural network learns a negative mass or learns an incredibly high value for your inertia. Can happen, yeah? But maybe then this value is not physical anymore. So then maybe it's underperforms when generalizing out of what you see during training. So we can constrain parameters. We can do this in different ways. Yeah, we can, of course, penalize its value in the loss function. So in the form of a regularization term, if we want a value to be small as possible. Or otherwise, we can act on the architecture of the model, the neural network, and we can use actually some artifacts, some equations to constrain the values of some parameters. So you see, for example, here we use the symbol of a sigmoid, and it's exactly what we use here. So z is our unbounded parameter, if you want. We can feed this to a sigmoid that is bounded between 0 and 1. So in this way, our parameter will be bounded between 0 and 1. But in reality, maybe we want the parameter to be bounded between -5 and 10, as an example. And then we can use an upper bound, phi with the bar, and a lower bound, phi underlined. And if we use this simple relation, we have, by default, we have for free that our parameter in output phi hat of u will be bounded between an upper and lower bound. Okay, so this is the simple way in which acting on, so this equation then becomes part of the neural network, yeah. So it becomes part of the model somewhere. And this is a simple way in which you can put bounds on your parameters to preserve physical meaning, supposing that we can give one to them. Yes.
Put out some example for the mass in this case that is not
yes. Exactly. Yeah. Good point. Yeah, indeed. So you can think that z in this case is our mass if the mass is a learnable parameter, and then the lower bound would be maybe something greater than 0. Well, maybe we know the mass already, right? For our system. In some cases, we don't know it because maybe it changes over time, and then we need to learn it. Yeah, exactly. Maybe if it's a case of a truck that gets loaded and unloaded, then we want to estimate the mass, but we have some bounds. Yeah. For example, we know the unloaded truck weighs I don't know how many tons, but we have also an upper bound, and then we can constrain it in this way. Yeah. Because otherwise it may happen that you go out of the range, significantly out of the range during training, and then it's an overfit typically, yeah, because maybe it's good to overfit the data, but then strange things may happen when you generalize.
Go back to the
Yeah.
connection. I want to say something
Yes.
related to the connection. Here seems very simple now. I mean, I just put a plus there, so it's. But there is something that is related to what I said yesterday about sparsivity. No. Here I could put a layer, no, another layer that just mix up the others, no. Is a possibility, no? It's, I don't know what is going on, I put a layer there. Putting a layer, I increase the number of connection, no? Remember what I said yesterday, so commonly the sparsivity helps the learning, you know? And also, if you know what are these terms, is unusable to put a layer here, because you know for sure that it is additive. Okay, so you remove connection, you help the learning, and also you get something that is physical. Okay, so it is very simple Plata plus here, but it's very powerful again, because you are reducing the number of connection of the network and you help the network to learn the right things. Because if you put a layer here and you learn there is some correlation between these two forces, it is wrong. Okay, so it is right that there is no any interaction between these two forces. Okay, so it's simple but it's powerful in the same times.
Yes.
Okay.
So yes, all these things go in the direction of constraining and designing the architecture in a certain way. But these are very general principles. I mean, these principles could apply to many approaches actually in the literature. They do apply to many approaches in the literature because there is an increasing interest of the community in these approaches. Yeah, okay. And then as a practical guideline, we can start from to design this type of neural networks. We can start from an imperfect physical model and neuralize its architecture, but we will see some examples.
What I want to say is that in some case, in many paper, maybe at some point they just say, yeah, and this I had a plus, and it's just a line in the paper there. But to make this plus or this specific layer, they decide maybe the architecture in some way that are something that sometimes is not highlighted in the paper, okay, but they have in the details. So the heavily stated in the details. So maybe they are applying some concept that come from physics. They are embedding some knowledge in the network to help the learning, but they are not highlighted this. Okay. So sometimes happens. So maybe there is a paper more general there. They say that I'm using neural networks, but then they say, yes, neural network, but I use activation function a sigmoid because is more physical. I add this, I divide it to networks, and then they are embedding physics to help the learning. So yeah, sometimes it's happening. So
yeah, there is indeed an increasing literature on these topics. And this is indeed general principles, but then
we try to give a more
yes, and then we would like to, based on the general principles, propose one particular implementation or one class of implementations that builds on top of these principles. And this is what this is indeed a general approach for dynamics learning of physical systems, yeah, or at least we would like to frame it in this way. Using what we call neural compositional modules, okay, or based on neural compositional modules. And so the idea here is to describe a physical system or learning the dynamics of a physical system by composing indeed some neural modules, neural compositional modules psi, we can compose them using some operations. And the inputs here are, okay, UK. This UK is a past history of inputs for the past n+1 time steps. We can have some scheduling variables, ZK, that tell us how the dynamics basically changes as a function of these scheduling variables. And the output is simply YK at the current time step. So it's the description of a discrete time dynamical system. And here we have indeed a quite general composition of these functions psi. And let's be a bit more precise. So here we have a composition which we can call F of the functions psi I. Each of these functions is functions of U and Z, so inputs and the scheduling variables. And what about this function F? Well, this function F belongs to the set, this set C of O. And C simply means a combination or a compositional operator. And the set of operators is sums and multiplications. So in other words, very simply, the functional F is simply telling us, please combine the modules psi using either sums or multiplications in whatever way, okay? And actually not in a random way, but in a way that satisfies your physical intuition, as we're going to see later. But this is the very high level view, right? So inputs, past history of inputs, scheduling variables, output, and then some neural compositional modules combined in a certain way with sums and multiplications. Very high level. And now the question is, of course, how to design psi, right? Is there some rules? Yes, turns out there are some rules that we propose. This will be the final expression. Looks a bit complex for the neural compositional modules, but let's get there gradually. So let's take a step back. Let's start from understanding what are the inputs and outputs of our representation. And to do that, let me start from a general physical system described by a nonlinear time invariant state space model. Okay, very, very general. Okay, so F is our state map, and H is our output map, depending on state and control. So I think you've seen it a lot of times in courses. And this can be a nonlinear system, of course. Yeah. Then let me substitute the first equation. So the state X, K, let's take it from the first equation and let's plug it in the second equation here. So H becomes H of X, K, UK becomes H of F, right? Because X is taken from the first equation. So here we have xk minus 1, uk minus 1. And let's do it recursively, right? Then xk minus 1 can then be a function of xk minus 2 and uk minus 2, right? So we recursively feed the first equation into the second. And we come up with this representation, right? So we come up with the representation that the output, yk, is basically a function. Then we have this functional g that is different from A. It is a combination of H and F. And the inputs here are past values of control inputs UK up to UK minus n, where we stop with our substitutions. And then we still have the initial state, xk minus n, right? So here we have xk minus 1, but when we continue recursively, we will have xk minus n based on where we stop with our substitutions. Okay. And it turns out, so ideally, you can go back to minus infinity. By doing so, you can continuously substitute the states. But it turns out that if you take n long enough, right? So if you go back again, if you go sufficiently back in the past, if you move backwards sufficiently, then your initial state doesn't matter anymore, or its effect is negligible. So you can think, if you're driving your car, you start accelerating with your car, and you start from an initial speed, maybe, right? But after a while, you will reach your maximum speed, right? For example. So after a while, your initial state, your initial speed won't matter anymore. The only thing that matters is that you kept on pushing the accelerator pedal. Right, so the initial state intuitively for a dynamical system is related to the free response. So in the case in which I remove my input, then my system will evolve based on its state only. But, and this is called the input-free response or the free response of the system. But if there is an input, then you can describe the output yk only as a function of the past history of the input, u, forgetting about the initial state as long as this window is long enough. Okay. And this holds for any dynamical system, for any nonlinear system. It's something very general. You can simply derive this as we've shown here. So the forced response at the end dominates. And yes, indeed. So here we can simply remove the initial state if we go backwards enough. And so this is our new representation. And what can we say on top of that? Yeah, on top of that, we can say, well, let's suppose that our representation G is also changing somehow. So we cannot describe our full system dynamics and our full domain with only one function G. But maybe we need to be a bit more careful and say that we have not only a function G, but we also have, so not only a past history of inputs, but also some scheduling variables. Because indeed, our dynamics may be domain, maybe operating regime dependent. Okay, so for example, our lateral vehicle dynamics, if you're driving a car, if you steer at low speeds, you will get a certain response. If you steer on the motorway, driving at 140 kilometers per hour, and you try to steer, the vehicle behaves completely different, right? So you may think of the scheduling variable in this case as the speed of the car, or the gear, right? If you accelerate in second gear, it's very different from fifth gear, right? So scheduling variables, and at the end we have the full expression of the neural compositional module NCM with what we called psi before, right? So we have the full system psi, which is a function of its past inputs, history of inputs, scheduling variables. By the way, we can also have a past history of scheduling variable if we need that, and we will use that. And then we have our output yk. Questions up to now? Okay. So again, this is very general. We're not saying anything about psi. Psi can be whatever, neural network, analytical functions, whatever. We're just talking about inputs and outputs. Yeah. And then what about the internal architecture of psi, of this functional? So let's start from, let's get there gradually. Okay, let's suppose our physical system is linear. Okay, if the system is linear, we can write psi in this form that maybe some of you have seen. So this simply means, let's take the discrete time transfer function of the system. Let's call it gamma. So I think you've heard of transfer functions, yeah, in the frequency domain. Well, it turns out you can actually convert them to time domain, to discrete time domain. And this operator here, this product, this is not a product, it will be a convolution if you want to be rigorous. So the output y would be the convolution of gamma, which is the discrete time transfer function, times the input u, okay? And you can actually expand this convolution very simply. It becomes a sum from I equals 0 up to infinity of some coefficients gamma I. These are simply coefficients, numerical values, times your past inputs, okay? From time k, when I equals 0, to basically minus infinity. So back to the Big Bang, yeah, right? To minus infinity. And this is called an infinite impulse response system, also in the system ID community. But do we really need to go back to minus infinity, back to the Big Bang for a dynamical system? Probably not. Yeah, we can stop somewhere, and then it becomes a finite impulse response system. So basically, here we don't have infinity anymore. We have n, and it turns out we can do that. Yeah, it's feasible for practical physical systems. It's always like that, right? Even if they are linear, especially if they are linear, we can model them like that. Oh wait, then this gamma I is simply a numerical value. Then we can call it G of UK, and G in this case is simply a fully connected layer. So a fully connected layer in a neural network is simply a layer that performs a linear combination of its inputs. So if you want, you can see it as a vector of weights. So this fully connected layer G receives as input a vector of weights, past history of inputs, takes a linear combination of them, right, with these weights gamma I, and simply gives us the output yk. Okay, so you can see, you can write it mathematically very shortly like this. But you can also interpret this as a small neural network already, right? So a fully connected layer is simply a layer that takes a linear combination of its inputs. And it's a learnable linear combination, right? So we actually learn the values of these gamma I, of these coefficients. Okay, and yeah, questions up to here? So I'm simply rewriting it here. If the system is linear, we have a linear combination. What happens if the system is instead not only linear, but locally linear? So the system is maybe non-linear, but locally it behaves linearly. Well, many systems do like that. And in this case, the gamma I become not only coefficients, but become maybe functions. So their value is a function of zeta k, where zeta k is our scheduling variables. Again, they can be discrete time, they can be continuous time. Maybe they can represent, for example, the speed of the vehicle, and then it's continuous time. For example, if they instead represent the gears, when we change the gears, then it's a discrete time scheduling variable. But yeah, very intuitive, I hope. And for example, yeah, the U, so okay, it can also be that the set of inputs is included in the set of scheduling variables. So for example, the speed can be both an input to our model, but also a scheduling variable. It may happen, right? Because maybe we want to estimate here the longitudinal acceleration of the car as a function of its past speed values. But then a single linear system is not enough to describe the nonlinear dynamics of the car. Maybe there is no linear drag, no linear effects. And so we still need to use the speed as a scheduling variable as well. So maybe the system is linear from 20 to 40 kilometers an hour, and then also from 40 to 60, but it's linear in a different way. Right? And okay, these modules G, okay, so in this case, G becomes a function of Z and U. Okay, it's not a function of U anymore, it's a function of U and Z. And this can be very general, okay? Here you may tell me, yeah, go ahead and use a certain type of scheduling. We propose a particular type of scheduling, or you know, of activation, yeah, what we call here activation. So we say, wait, let's still go back to the notation in which G only depends on the input. And then we have separate activation functions phi, which are only a function of Z, of the scheduling variable. And then this is the representation, right? So here we had an only function G. Now let's have a bunch of functions G from 1 to m. So a bunch of parallel the representations of G. Each of them has the same expression, mathematical expression, but maybe different values, different weights. And then we have that Z is entering these activation functions, phi1, phi-m. Each of them is basically activating the input based on their local activation. So maybe phi1 is activating the input only if its argument Z is between 20 and 40 kilometers per hour. And then phi2 is activating between 40 and 60, and so on until we cover the whole domain. Okay, maybe phi-m is between 150 and 200 kilometers per hour.
Or gears.
Or gears, yeah, exactly.
Discrete
So
variable. So
maybe, yeah.
Each model here is try to fit a specific gear of the car. So this is an activation function that activates for the first gear, second gear, third gear. So,
yes.
Yeah.
So indeed, yeah, we can also have different gears. But the idea is, okay, let's use different activation functions to activate each of the models. Okay, and this symbol here is simply the element-wise product, because these are vectors. These are also vectors. So here we take the element-wise product between phi1 and u, and here we take the element-wise between phi2 and u. Okay, so they are all, if you want, they are all row or column vectors.
Also,
Okay.
zeta is a column.
Yeah, zeta can also be a column vector. Yeah, but later we will see more about dimensions. These functions here can be, the activation function Z can be trainable or frozen. So in some cases, you may want to say, at least if they are continuous, if their input is a continuous variable, like the speed, you may say, well, let me train them. So let the neural network decide where the system is actually linear, in which ranges of Z the system is actually linear. For example, it's not from 20 and 40 kilometers per hour, it's from 20 and 30. And this is something that the neural network can learn. Otherwise, if we want to be more cautious, or if we know something about the system, we may say, no, wait, I want them to be frozen. I don't want the neural network to learn this type of information. This is a design choice. Okay.
It also depends
yeah.
on the distribution of the data that you have.
Yeah.
Because think that you have a unbalanced distribution of your data, and maybe most of the data are activating the first one. If you give the network the possibility to move this activation function, the network may decide to put all the activation function in the region where are more informative, where they are helping to gain some minor percentage of the fitting. But in that case, then you lost completely the other part, okay, where maybe you have just some points. Instead, if you decide a priori this activation function, you may solve some issue due to the unbalanced data set. Because if you decide to keep this activation function in a specific region of the space, doesn't matter if you have just 6 points, but still you try to fit this part of the data set.
Yes.
Okay.
Yes. So what may happen is that if you have all the data concentrated between 20 and 40 kilometers per hour, but you still want to learn the dynamics from 20 to 100, then of course your neural network, if the functions are trainable, most of them will be squeezed towards 20 and 40 kilometers per hour, because all the data is there. So we need more flexibility to learn the data behavior from 20 and 30. And then maybe no activation function, or only one activation function, would be from 40 to 200. Yeah, this can be good, but in some cases you want to. Yeah,
if you know that you are a good balance data set, you may decide to keep the network to learn where it's better to put the activation. Otherwise, if you have looked at the data set, you saw that maybe it's not balanced, maybe it's much more conservative to decide the value of the activation function. So be sure that at least you try to
yes,
fitting,
to
you know,
cover
the range.
exactly.
Mm.
Yeah, indeed, yeah, good point. And yeah, there are some common choices for the shape of these activation functions. So, for example, in this case, we show triangular activation functions. So we decide that this is our scheduling variable. This is omega in this case, which can be the yaw rate of the car, whatever. And we decide that we want to predefine the shape of the functions. The important thing is that they all sum up to 1. So the sum of all the activation functions should be 1. Because if it's not 1, you're basically saying that one channel or one model is more important than the others, right? You're creating some imbalance among the different modules. While we want to keep the sum equal to 1, also each activation function should be greater than 0. And if you see these functions, they are designed in such a way that they all sum up to 1. So the blue one is active only from 0 to half of the domain. The second one is also active from 0 to half of the domain, but also then remains active until the end. Okay, so in each part of the domain, if you see, we have 2 activation functions that are positive, that are greater than 0. So in this case, it's the red and the blue. In the second case, it's the red and the yellow. And at the end, when we reach our maximum speed, there will be only one model that remains active, yeah, basically. So this is one design choice, but they could also be, because in this case, our z is a continuous variable. It's a velocity, so we want to be continuous also with our activations. If instead we have discrete variables like gears, first, second gear, third gear, then maybe it doesn't make sense to use triangular. We can use rectangular, right? So we want to be constant from the first to the second gear because only one gear can be active at a time. And then this function can go to 0 because we have the second gear that gets engaged, and so on, yeah? So in that case, a function is either 1 or 0 and no intermediate piecewise linear values like here. We can also use Gaussians, yeah, or other functions. So this is the system that is locally linear, we said, right? If the system is locally linear, we can represent it in this way, like a combination of linear models, a local combination. And these layers are, once again, they are fully connected layers. Each of them, G1, GM, is a fully connected layer. So it's basically they're learning a linear combination. You find it here, a linear combination of the output of this part here. Okay, where U again is the past history of inputs. The phi is regime-dependent activation functions. By the way, each of these phi j from j that ranges from 1 to m, each of these phi j is a vector, as we were saying before. So here we want to take the element-wise product, not the vector product. So we want to multiply the individual components, like first component times first component, second times second, last times last. So this is an n+1 vector. This is also an n+1 vector. You take the element-wise product among their components. So this is a row vector at the end. Sorry, this one is a row vector. And this one will be a column vector. So row times column, we have a scalar at the end. Yk is a scalar, right? So yes, G is actually a column vector. We have a transpose here, an n+1 column vector. And indeed, we can interpret them as neural finite impulse response layers. So each of these layers is learning the finite impulse response of the system depending on its regime, right? So we have different responses of the system depending on the values of the scheduling variables. Okay, questions? Yes.
Basically, this is very similar to interactive multiple models.
Exactly. Yeah, it's related. Yes.
But you can learn part of the.
Exactly. Yes. So maybe towards the end or tomorrow, I will also show you a parallel with the adaptive neurofuzzy models and other also interactive models. So yes, there is a relation among these philosophies, but here, yes, we have actually learnable components inside, and actually this is not the whole story. Then we will be adding other blocks here that will appear. But yes, definitely you're right. Then there is a relation with interactive models. Yeah.
These are interactive linear.
Yes, exactly. Yeah.
Can you also do nonlinear?
Yeah.
Yes, exactly. We will get there in a second. Yes. Maybe, yeah, I will maybe conclude this part so we skip the other break. Yeah, and then we finish early. Yeah, maybe in 10 minutes we close. So indeed, if the system is locally linear, we have this representation. But yes, this is not the whole story, right? Because we can have, for example, an input nonlinearity. This is a type of nonlinearity. So instead of having nothing, we can have an input nonlinearity. In this case, these functions f are just pre-processing, if you want, or are processing the inputs. We can have different functions for each of the locally activated branches.
You can have the same or different.
Yeah, we can have the same or different functions in different branches. But the question is now how to design them. Yeah, so we understood how to design G. They simply perform linear combinations of their inputs, and they learn the response of the system. But what about F? How to design them? Well, it turns out that here we can actually encode some physics priors. If we have some prior knowledge, domain information, whatever, we can try to incorporate it in the function set. For example, this can be input mappings, yeah, so nonlinear input mappings, like in the case of the aerodynamic drag. If you think this layer maybe is learning the aerodynamic drag, this is proportional to the square of the speed, right? So here we can simply take the square of the inputs if you want, in a very simple case. In more complex cases, it can be static mappings that we know of the inputs. For example, here we want to compute, I don't know, if U contains the angular velocity and the linear velocity of our mobile robot, then here maybe we want to compute the lateral acceleration, and so we take the product of the angular and linear velocity, and then we give this to the rest of the branch that maybe estimates the lateral forces using the lateral acceleration, and so on. So here we can actually embed physics priors, and we'll see examples tomorrow. So here we can use our expertise in the design of these blocks. But in some cases, okay, in some cases we know we have physics priors. In some other cases, maybe we don't know, or we know, or we know partly. So we can have maybe limited physics priors. Like we know in the case of a manipulator, again, like before, the dynamics can be a combination of trigonometric functions, yeah, but saying how can be complex. So in this case, one possibility, again, related to topology learning, is to combine trigonometric functions with equation learning. Okay, so you know you want to combine here trigonometric functions. These are in your dictionary, but you can let your f functions inside your neural compositional module learn the exact representation, or learn the best representation using a set of dictionary functions that you predefine. Yeah. So there's a lot of possibilities we can use in the design of the F blocks, while still keeping the rest of the model, interpretable, let's say, or with its formulation. But in some cases, we don't even know that we don't even know a bunch of dictionary functions to use. In this case, what can we do? Yeah, we can simply learn, for example, a Taylor approximation of the nonlinear function which we don't know. That, for example, it can be a second order, first order, whatever, Taylor expansion or Taylor approximation of our unknown nonlinear function. And then in this case, it's like a second order Taylor with learnable A1, A2, A0, A1, A2. So each of these F1 up to Fm can have different learnable weights in this case, right? So each of them learns a different nonlinearity and then uses it in the rest of the model. Questions or ideas or course or more general machine learning models? Yeah, we can also say no, a Taylor expansion is not enough. We use the general purpose neural network in each of these F1, Fm modules. Yeah, we can still do that. So yes, this is the case of locally linear model plus input nonlinearities, yeah, which still, I mean, arguably describes a broad class of nonlinear systems. Because indeed, you have flexibility in the design of the F modules. You can embed your own knowledge. You have the scheduling variables, so you can learn different dynamics for each operating condition, and you have the G functions that learn your dynamics, the transient response. So it's still arguably flexible. But in some cases, the system is just nonlinear, fully nonlinear. This is actually the general case. And in this case, what can we do? Yeah, we can add, so we can simply add a residual block here. This can be a general purpose residual block, takes as input again our inputs U, adds them additively, additive correction outside of everything, on top of everything. And this is a form of residual learning, if you want. And so we would like to propose this structure here as the structure of our neural compositional modules psi, which we mentioned at the beginning. So in general, they combine a past window, a past history of inputs, scheduling variables to compute the output. How they do it is with this proposed design. Okay, so some input functions to model the nonlinearity, activation functions to capture the regime-dependent dynamics, and the G functions to actually learn the transient response. And of course, some residuals because our system is never perfect. So in practice, this is the structure we will see also in many of the examples we'll see tomorrow. And again, this is the structure for one compositional module. Okay. Yes, I don't know if we want to see that tomorrow or we can also close. Yeah. So yeah, there are some extensions. Yeah. So in general, here we have one input. Okay, one input like the steering angle of a car. But in general, our system is multi-input. Yeah, of course, it's multi-input. So we can have P inputs here. So from U1 to UP, for each of them, we need to take a past history of them. And we stack them together in the matrix UK. In general, we can also have multiple scheduling variables. So by the way, this Z, you see it's actually in bold, so it's a vector. So even if we have only one Z, it's actually a vector from ZK-n to ZK. But in general, you can have more than one. Like you can use your gears, you can use your speed, you can use whatever.
Yeah. The only things that you need to remember is this function is commonly not works in time. Okay, so it's preserving the time information for the next step. Okay, so the time information is processed by the linear operation there, and here you are making maybe a composition between the variable that you have, but you are not working in the time domain. Okay, commonly is what we do is this. Okay, so you have a function that works merging, operating on your input variable and output a sequence in time of that a new variable, and then this time variable is scheduled by the phi function, and then is processed by the linear operation that is mesh up the
Yes.
time of the time domain.
Yes, indeed, yeah.
Split
So
time
there
domain.
is, yes, indeed, there is a separation. So indeed, so these G functions actually operate on the time domain, so they squeeze the time domain,
Yeah.
because up to here we still have a vector, right? Up to this point we still have vectors that are then compressed by this operator into scalars, and then we sum the scalars. While these are actually vector functions. Yeah?
Yeah.
So you see these ones are not in bold because they're not, their output is a scalar, while these ones are in bold because their output is still a vector.
Yeah.
Yes. Yes, so in general, we can have different scheduling variables as well. Like the first one can be called Z1K. Okay, this one in blue. The last one can be ZQ. Okay, like this one in pink. And then ZK, so this variable here is simply stacking them all together in a big matrix. But then how do we do with the activation functions? Yeah. Because then they become matrices as well. It's a mess, yeah. So here we can actually use a simple rule. So we can say if we have a Z that is multidimensional, then phi1, for example, is simply a product, again, element-wise product between the individual functions for each of the scheduling variables. So it's the element-wise product between phi1 evaluated with the first scheduling variable, like with the gears, times the last one, which will use the speed or whatever. And we take the element-wise product of everything. Same for all of them. So this was for phi1, but for phi m, of course, it's the same, with m denoting the total number of regime conditions that we want to consider. So again, this was the example like before. Yeah. So this was a one-dimensional activation function phi. In this case, z1 was equal to omega, because this is the variable here, to an angular velocity. In the multidimensional case, we need to take the element-wise product between this one and another one. So they become actually, if we have two dimensions, yeah, exactly, it becomes a matrix. If they have two dimensions, like Z1 and Z2, then instead of triangles, we will have pyramids, yeah? So the pyramids, because we have one variable that is in this dimension, and another one that would go out of the blackboard, and when you take the dot product between them, you have dot product between two triangular functions, so you have a pyramid at the end. Right.
Thanks to the property of this function, the function that you obtain still have the same property. So if you sum over all the space, the sum is always 1. Okay, because the property holds for all the functions. So
yes,
if you multiply them together, you still get the same property.
Exactly. So there is a reason why we take here these operations. That's actually to preserve the fact that they still sum up to 1, because we don't want to have an imbalance among the branches. And we still want to have them always strictly positive, yeah, or greater than 0. Okay, I think we can maybe stop here for today, or maybe, okay, let me just say the last thing. The last thing is, okay, this is just the structure of one neural compositional module, right? This is the most general case. Multidimensional inputs, multidimensional scheduling variables, input functions, F, output functions, G, activation functions, phi, most general case, residuals are. But then, okay, this is one neural compositional module, but do we need to, I mean, can we use only one neural compositional module? Maybe yes. Or maybe can we still combine them to obtain even more flexibility and even more learning capabilities? Well, yes, in principle, we can combine them because, for example, each of these phi functions, psi functions, can be specialized to learn, for example, one part of the system dynamics. Like one learns the lateral dynamics, one learns the longitudinal, if it's a mobile robot, and so on. So, for example, here we have different psi blocks, different neural compositional modules to learn the effect of independent forces and moments. So we just give the same inputs to 3 or more neural compositional modules. Each of them estimates one force or one action, and then we just simply take the sum because we know they are independent forces, like in this case, yeah. Or we can learn one part of the dynamics. Yeah? Another case in which is the case in which we want to model or to learn separately the steady state and the transient dynamics of a system. We can still do that, right? So we can have, so in this case, we're taking the sum. In this case, instead, we're basically cascading, putting them in a cascade connection. So the first psi1 is learning the steady state dynamics because we design it in such a way. The second one can be learning the transient dynamics, and then we stack them together. So in general, we said at the beginning we can have sums, so plus signs, sums and multiplications, or cascading operations among different neural compositional modules. And we argue that by doing so, you are quite flexible to model, to learn the dynamics of physical systems. Yeah, so we're still in the setting of dynamics learning of physical systems. We argue that with this design, we are flexible enough. And tomorrow we will show you some applications for that, both with the slides and using using our open source PyTorch-based framework that speeds up the design of this type of neural networks, yeah, that we call model-structured neural networks. And so tomorrow we're going to see some applications. Yeah, very last thing, the pros and the cons of using neural compositional modules. Well, of course, yeah, one of the pros is that you're still having a modular design, so you can, if you do things carefully, you can still interpret the trained weights of f and g of these functions. And tomorrow we will see an example in which, or some examples in which we can actually give a physical meaning to their value, which is a nice thing, I think. We can split the task complexity. Yeah, so if we have different subtasks within our big dynamics learning problem, we can do that with different modules, neural compositional modules. And we will show that in this way we can outperform, especially the sample efficiency. So the sample efficiency of black box general purpose networks, because indeed we are basically designing an operator that learns with a certain structure the dynamics of a physical system. So of course, some design effort is still required, so no free lunch at the end. If you want to do things carefully, or I mean, if you want to be really sample efficient, you may want to embed some prior physics priors or prior designs also for the FJ modules for the input functions. I mean, you can also use general purpose networks, but if you want to make some extra effort and inject physics knowledge there, this typically gives advantage, but it comes at a price. Of course, you need to sit down and think what to do. Yeah.
I want to say one thing related to this. We present here in this order.
Yes.
So in the order of the input function is always the nonlinear function and the output is always the dynamics function. But we have at least one example where we do the opposite. We swap the input, so the nonlinearities and the nonlinear function, because maybe you know how merge physically the output of the dynamics, not the input of the dynamics. So, I mean, here was a matter of simplicity or a matter of explain our approach. We stick on input function nonlinear, output function, the time domain operation, but in principle, you can also swap. The difference is that if you swap, the phi function will output in, so zeta must not have the time domain information, okay? Because you compress, you squeeze the time domain before the activation function.
Yes.
Yeah.
Yeah, in that case, so you can also decide to swap f and g, and in that case, you are compressing the elements of the vector, of the input vector u already here. You're compressing them into a scalar, and then these functions here become also scalar. They're not vectors anymore, and this one is another scalar function. This is an alternative, but this one is actually the most powerful design, probably in general. So we wanted to present this case, and tomorrow we will see some applications. Good, yeah. Questions on these topics? Yes.
Swapping these two blocks, is it really equivalent? Because I suppose that if you have a time window also on the activation function, you consider the activation function that depends changing time.
In time.
Yes, exactly. Yeah. So the question is if it's equivalent to swap f and g. I mean, if you get an equivalent design, and no, actually you're right, you don't get an equivalent design, so you get.
I don't think that you can get an equivalent design.
Yeah.
Because here you have a nonlinear function, no, in general. So if you swap, commonly
Yes. So you get actually a different model at the end, because you lose because you lose some degree of flexibility. Yeah.
What we use the approach to swap in particular in one case when the activation function was discrete, was the gears.
Yes.
In that case, before we manage the time operation, and then we activate the specific activation function for the gear. In that case, have a meaning because there is no reason why when you change the gear, you are affected by the gear that was activated before. So you just are completely. So the dynamics of the engine now is filtered by the new gear instantaneously. Okay, so there is no reason to keep in memory what's happening for the other gears before.
Yeah, so
arguably,
yes, if we have a discrete activation or a discrete scheduling variable, then one can also swap them. But yeah, we also don't want to create confusion here, so let's keep this as design. Yes. Yeah.
To see how you can have these and G.
Yeah.
If I don't, these are not dynamic anymore in the Marx structure.
Yes.
Example that we put to.
Yeah. Good point.
Yes.
Yeah, it's indeed a good point. So
some statical
yes.
base.
Yes.
Yeah. And the G is just some information.
Yes. So yes, the point is, if we can also add or plug in here autoregressive, right, arcs, autoregressive models, and yes, in principle we can do so. In principle, we can also feedback yk back to the input if you want, or back to some parts here inside the model. This is another possibility. Yeah, we're not showing it here. So technically with this design, we're not doing autoregression, but it's an extension that you're right, we have used sometimes, especially when we do control. So this is a structure we present for dynamics learning, but especially for control tasks, you may need to consider also, I mean, it can be helpful to have autoregression inside, but in principle, we can use it also for dynamics learning, yeah. It's just, so just if you follow this formulation mathematically, how we derived it, then the autoregression does not appear in this formulation. But if you want, it can also be part of the residual block, right? So the residual block, instead of being just a function of the inputs, of the past history of the inputs, could also be a function of the past outputs. So it could also receive past output values and compute some residual correction based on them with an autoregressive model, if you want, yeah. This is one possibility. It would be an extension, yeah, let's say. Yes. Yeah. Yes. Other questions? Yeah, also from online, of course.